In this video note, we shall look at solving one of the exercises towards the end of the chapter. This is described as a challenge exercise, so we shall assume that you are comfortable with most of the material that has been covered up to this point. The exercise involves creating the source code for a Java class from scratch. This is something we don't usually expect in the exercises, hence its more challenging nature. If you are not ready for this video note, then we recommend that you defer watching it until you've had the chance to do some more background reading and to get a bit more practice. The main purposes of this video note are to highlight the importance of documenting code as you write it and to maintain a consistent layout of your code. We also illustrate the value of making relatively small changes and testing often. The exercise asks us to create a new project called Heater Exercise. To do this, we select Project, New Project, and then navigate to the folder where we want to create a new project folder. Enter Heater Exercise in the File field and select the Create button. We now have a new BlueJ project with a class diagram that only contains the project description document in the top left corner. The exercise asks us to edit the description, which we can open in the same way as we would a class. We see from the title of the window that the description file is called readme.txt in the project folder, and that it already has a template in it for us to complete. So let's do that. We might not be able to complete everything at this stage, but we can always come back later and update it as necessary. Filling out this file is just the first of many points at which we shall be taking care to ensure that the programs we write communicate well with anyone who has to read them. While these things all take a little extra time, the overall improvement in the quality of the work we produce will be worth the effort. Now we are ready to create the class, which is to be called Heater. Select New Class and enter the name Heater. Remember to use a capital letter. Don't worry about the list of possible class types. By default, class is selected, and that is what we want. We can move the class icon on the diagram and resize it if we wish. Looking inside the class, we find that there is already some source code in there. Note that if you're following these video notes while studying a course, then your teachers might have made some adjustments to the default contents of the class, and you might see something different from what we have here. Nevertheless, the steps we take should be fairly similar. What we have here is actually a valid class definition, which you'll see if you compile it. However, for this exercise, we prefer to start with a clean sheet and remove all the contents of the body of the class. That way, you'll get to see in detail how to create a class from scratch. What we're left with is a class comment, a class header, and an empty class body. In fact, even this is a valid Java class, as we can see if we compile it. We can even create an instance, although of course the object has no methods, and the inspector shows that it has no fields. Nevertheless, what we're doing here is illustrating a useful discipline. Whenever we make a significant change to the source code, it's worth checking that the code still compiles. If it does, then that's what we want, but if it doesn't, we've found out something useful and will be in a good position to fix the error. If we always adopt this principle, then we shall know exactly the area to look for the error, because it will almost certainly be somewhere local to where we made the change since we last compiled. As you can see, recompiling takes very little time, but this discipline will save us a lot of time hunting all over the place through what might be quite a lot of source code. It's tempting to get writing code straight away, but let's not forget the discipline of making our classes readable. Our first task should be to edit the class comment and say something about the class, who wrote it, and give it a version number. While it's always tempting to skip this bit now and plan on coming back to it once the code is finished, experience suggests that this rarely actually happens. With that done, we can now start to add some code. The exercise asks for a field called temperature, whose type is double precision floating point. If you're not sure what that means, you can find information about it in one of the book's appendices. So we add a field that follows the pattern you should now be used to: private, double, temperature. But let's not forget to include a comment for it. Once again, we repeat the discipline of recompiling following a significant change, because an error would be very easy to spot within such a small area. Again, we can create an instance if we want, and just check that this version does now contain the field we just defined. These are simple little things to do, and we don't expect any of them to fail, but if we do find something that we hadn't anticipated, then the benefits are enormous. Don't be tempted to type the code in for the whole class before you select the compile button for the first time. Next, we need a constructor that doesn't take any parameters, but sets the temperature field to 15. Let's do that in two stages. Firstly, a constructor with an empty body, not forgetting a comment for it too, of course. Then compiling once again. Now we can add the assignment to the temperature field. Now we should expect to see a significant effect in the objects we create, so we do that and bring up an inspector to confirm that the field has the correct initial value. Why do we bother doing this? Isn't it obvious that the code is correct? The problem is that many of the errors that are the hardest to find are the result of incorrect assumptions or little oversights. Let's illustrate this in practice. Suppose the constructor was actually expected to take a parameter that provided the initial value of the temperature field. We might have written it like this. Since temperature is the obvious name for this value, that's what we'll call the parameter. Then, in the body of the constructor, we assign the parameter to the field. Let's go through the seemingly pointless exercise of compiling, creating, and looking at the inspector. Lo and behold, something is wrong. The field doesn't have the right starting value. How can that be? There must be something wrong with the assignment, but we didn't expect there to be, otherwise we wouldn't have written it that way. Going through that very short cycle of compiling and testing has forced us to look afresh at code we assumed to be correct anyway. But the great thing is that we know exactly where to look for the error, at the assignment. And when we're forced to look twice at something we thought was correct, we're more likely to spot the problem. You may already have spotted the error as soon as you made it, but this is exactly the sort of error that many people make when taking their first steps in learning to program. It neatly illustrates the form of blurred vision that creeps in when writing things that seem to be straightforward. The error is caused by having a parameter and a field of the same name. So the assignment is not actually from the parameter to the field, but from the parameter to itself, an operation with no effect. One way to fix it is to give the parameter a different name to the field. Let's put the error back in. Another way to fix it is to add a this prefix to the variable that is the field. That prefix can only be applied to fields, so now the variables on the two sides of the assignment are clearly distinct. However, our class doesn't actually take a parameter to its constructor, so we can go back to solving the original problem. We need to add two mutators, warmer and cooler, that increase and decrease respectively by 5 degrees the value of temperature. Once again, it's tempting to do both at once, but we'll do them one at a time and test after adding each. Notice that we apply the discipline of writing the comment first, describing what we're going to do, before actually writing the method. This again is a good discipline to apply. If we can't actually express what it is we're trying to do, we're probably not going to be able to code it. Calling the warmer method, we see the temperature has indeed been increased by 5 degrees. Now that we're happy with that, let's save ourselves some typing and use a copy and paste for the cooler method. We obviously need to make a few changes, and that's what we do. We compile it and test it again. But oh dear, there's something wrong. The temperature has changed to 20 instead of to 10. Notice that in testing it, we actually had an expectation of what the answer should be, and the result conflicts with what we thought it should be. That's always important with testing, to make sure that you have an idea of what the answer should be. Looking at the source code, we can see that we forgot to change the plus to a minus. So we fix, compile, and test once more. That's better. Job done. And actually it really is done. Because we documented and tested as we went along, the class really is finished. We don't have to go back and add comments in, or clean up the layout, or just check a few more things are working. We've done all that as we've gone along and saved ourselves a lot of time. In summary, we've seen how to create a class from scratch, making use of the source template that BlueJ provides to get us started. We've self-imposed a discipline of documenting as we code, which saves us from having to go back and do it afterwards. We've made relatively small changes at each step, and that's made both the finding and the fixing of errors much easier than if we'd tried to build the class in one go. There's really no time overhead in doing things this way. In fact, the approach actually saves on debugging time in the long run.